NASA's James Webb Space Telescope has hardly opened its eyes.
Today represents an exciting new chapter in the exploration of our universe.
We can also unlock the secrets of the Big Bang.
First of all, of hundreds of new stars that we've never seen before.
Many people believe the universe started with a Big Bang. While the theory is popular thanks in no small measure to the TV show with the same name, the basis of modern astronomy might be shaking as eminent theoretical physicist Professor Michio Kaku has finally proven the theory wrong, courtesy of the latest discovery by the James Webb Space Telescope. What did the Space Telescope discover and how does it support Professor Kaku's theory? Keep watching this video and see how Michio Kaku finally proves the Big Bang theory is wrong. Have you ever wondered how the universe began? Well, according to the most widely accepted theory, it all started with the Big Bang. But what exactly was the Big Bang and how did it create everything we see today? Let me tell you a story of how a tiny speck of nothing exploded into a gigantic cosmos of stars, planets, and galaxies. The Big Bang Theory says that about 13.8 billion years ago, the universe was in a state of extreme density and temperature. It was so hot and dense that even atoms could not exist. Everything was squeezed into a single point of infinite density called a singularity. This singularity was smaller than an atom but contained all the matter and energy that would ever exist. Then, for some unknown reason, the singularity started to expand rapidly. This expansion is what we call the Big Bang. It was not an explosion in the usual sense, but rather a sudden stretching of space and time. And as the universe expanded, it also cooled down. This allowed for the formation of subatomic particles such as protons, neutrons, and electrons. These particles then combined to form atoms, mostly hydrogen and helium. However, the universe continued to expand and cool for hundreds of thousands of years. During this time, gravity pulled the atoms together into clumps. These clumps became the seeds of stars and galaxies. The first stars ignited when hydrogen atoms fused together to release energy. This process is called nuclear fusion. The stars then produced heavier elements such as carbon, oxygen, and iron by fusing lighter elements together. Some of these stars then exploded in massive supernovas, spewing their elements into space. These elements then formed new stars and planets. And one of these planets was Earth, which formed about 4.5 billion years ago. Planet Earth was a hot and hostile place at first, but it gradually cooled down and developed an atmosphere and oceans. Life emerged on Earth about 3.5 billion years ago, starting with simple cells that evolved into more complex organisms over time. And that's how the Big Bang started the universe and life as we know it. Of course, this is a very simplified version of a very complex story. And the more complicated version says the events that followed the Big Bang occurred in multiple different periods, which is where the discovery by the JWST is causing a problem. Michio Kaku, who himself has written books on the origin of the universe, talks about the JWST's new discoveries and what they mean for our traditional understanding of the origin of the universe.
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
This is serious because some of the books written by Kaku will be affected, but Kaku talks about the problem further.
Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist 500 million years after the Big Bang that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen.
So let's make sense of all these. This is how it shakes out. The universe was a very dark place until about a few 100 million years after the Big Bang. There were no stars or galaxies to speak of. The universe was like a hot soup of particles, protons, neutrons, and electrons after the Big Bang. When the universe began to cool, protons and neutrons began to combine to form ionized atoms of hydrogen and deuterium. Deuterium was then fused to form helium-4. These ionized hydrogen and helium atoms attracted electrons, converting them to neutral atoms. At this point, the universe's composition was 3 times more hydrogen than helium, with only trace amounts of other light elements. This process of particle pairing is known as recombination, and it occurred between 240,000 and 300,000 years after the Big Bang. At this point, the universe transitioned from opaque to transparent. Light could not previously travel freely because it would frequently scatter off free electrons. However, light was no longer hampered because the free electrons were bound to protons. The era of recombination is the earliest point in our cosmic history to which we can cast any light. With satellites such as the Cosmic Microwave Background Explorer COBE and the Wilkinson Microwave Anisotropy Probe WMAP, we can now observe the cosmic microwave background. The cosmic dark ages then followed, a time period after the universe became transparent but before the first stars formed. Then, when the first stars formed, the dark ages ended and the next epoch in our universe began. But what caused the aforementioned fog? A variety of things can happen when light collides with matter. The light can bounce back off the matter as if it were a mirror, or it can pass straight through it as if it were glass, or it can be absorbed in some cases. Now, these special cases occur when the energy of the light exactly corresponds to an energy transition in the atom it is passing through. When this occurs, the atom absorbs a photon of light and uses the energy from that photon to boost the energy of its own electron. Now, there were no atoms in the first moments after the Big Bang. However, light could not travel very far because it ricocheted off free electrons at every turn. However, the photons no longer bounced around after the formation of the first hydrogen atoms. Furthermore, because most photon energies did not correspond exactly to a hydrogen transition, they were free to shoot off into space. That is why the cosmic microwave background, which dates from 380,000 years after the Big Bang, is often referred to as a snapshot of the universe. Now, continue forward a few hundred million years. The universe is filled with hydrogen gas, and the first stars are formed when the gas clumps together due to gravity. But here's the catch. Because stars and gas are made of the same stuff, much of the light emitted by stars has the right energy to be reabsorbed by the hydrogen that surrounds them. The photons never leave their cosmic neighborhood. The stars are obscured in a fog of hydrogen to earthbound astronomers looking back today. However, moving on, more time has passed. Galaxies continue to give birth to stars, and stars continue to shine. A photon can occasionally have enough energy to completely dislodge the electron in a hydrogen atom, ionizing it. Because this ionized hydrogen lacks electrons, it does not absorb light. As a result, starlight is free to pass through it. Given enough time, photons will ionize the majority of the hydrogen surrounding a galaxy, clearing the fog and allowing starlight to begin its long journey to us. And after the first stars formed, another change occurred. The first stars, according to the theory, were 30 to 300 times the mass of our sun and millions of times brighter, burning for only a few million years though before exploding as supernovae. These first stars' energetic ultraviolet light was capable of splitting hydrogen atoms back into electrons and protons, or ionizing them. This time period, from the end of the Dark Ages to around 1 billion years ago, is known as the epoch of re-ionization. It refers to the time when the increasing radiation from the first massive stars re-ionized the majority of neutral hydrogen. Now, reionization is an important phenomenon in the history of our universe because it's one of the few ways we can indirectly study the first stars. However, scientists do not know when the first stars formed or when the reionization process began. The birth of these first stars heralds the end of the Dark Ages in cosmic history, a period distinguished by the absence of discrete sources of light. Understanding these early sources is critical because they had a large influence on the formation of later objects like galaxies. The first sources of light serve as seeds for the formation of larger objects later on. Furthermore, the first stars to explode as supernovae may have collapsed even further to form black holes. The black holes began to consume gas and other stars, forming what is known as mini-quasars, which grew and merged to form the massive black holes found at the centers of nearly all massive galaxies today. However, the problem now is that the new discovery by the JWST, which Kaku was talking about, stands to shatter everything we knew about how the universe started and how galaxies formed. You might have to retake some high school science classes. The JWST actually discovered a group of galaxies from the beginning of the universe that are so massive that they should not exist. These 6 massive galaxies, which contain nearly as many stars as the Milky Way despite having formed only 500 to 700 million years after the Big Bang, have been dubbed universe breakers by the team of astronomers who discovered them. It's bananas. Co-author Erica Nelson, an assistant professor of astrophysics at the University of Colorado, Boulder, and one of the researchers who made the discovery, said in a statement, "You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have formed." Scientists don't know when the first clumps of stars began to emerge into the galaxies we see today, but cosmologists previously estimated that the process began gradually taking shape within the first few 100 million years after the Big Bang. According to current theories, these early proto-galaxies reached adolescence 1 to 2 billion years into the universe's life, forming into dwarf galaxies that began devouring each other to grow into ones like our own. Now, because light travels a constant speed through space, the further we look into the universe, the more distant light we encounter and the further back in time we see. The astronomers discovered that enormous galaxies had already burst into life very quickly after the Big Bang, when the universe was only 3% of its current age, by peering roughly 13.5 billion years into the past with the JWST. According to the researchers, the galaxies are so massive that they're in conflict with 99% of the cosmological models. This means that either the models must be changed or the scientific understanding of galaxy formation must be rethought. Now, every year the Milky Way creates 1 to 2 new stars. For the entire history of the universe, some of these galaxies discovered would have to be forming hundreds of new stars every year. If even one of these galaxies is real, it will test the limits of our cosmological understanding. And currently, all evidence points to these celestial objects being galaxies, but astronomers haven't ruled out the possibility that some of them are massive quasars or supermassive black holes. As Joe Lear, an assistant professor of astronomy and astrophysics at the Pennsylvania State University, in a statement puts it, "This is our first look back this far, so we must keep an open mind about what we see." While the data suggests they are galaxies, Lear believes there is a real possibility that some of these objects are obscured supermassive black holes. Regardless, the amount of mass discovered indicates that the known mass of stars at this time in our universe is up to 100 times greater than previously thought. Even if we cut the sample in half, this is still a remarkable difference. The Hubble Space Telescope's previous imaging of the early universe did not detect these giant galaxies, but JWST is about 100 times more powerful than Hubble. The $10 billion JWST launched in December 2021 to a gravitationally stable location beyond the Moon's orbit known as a Lagrange point. The Space Observatory was created to read the earliest chapters of the universe's history in the faintest glimmers of light. Light that has been stretched to infrared frequencies by billions of years of travel across the expanding fabric of space-time. The astronomers now plan to make a spectrum image of the giant galaxies, which will provide them with accurate distances and a better understanding of the chemical makeup of the anachronistic monsters lurking at the beginning of the universe. But what does Kaku think is the explanation for this new discovery?
When they're actually baby galaxies. Now, I personally think that the solution to the problem is these are not baby galaxies at all. They're actually monstrous black holes. Black holes that formed after the instant of creation. That's baffling scientists because they don't fit in the normal sequence of the birth of a galaxy. So I personally think that we're actually looking at monster black holes where perhaps new laws of physics are emerging. And again, if you can figure all this out, there could be a Nobel Prize waiting for you.
As Kaku suggested, the JWST actually recently spotted the earliest known black hole in the universe, and astronomers think even earlier ones could have swarmed the young cosmos. The cosmic monster could be one of the countless black holes that gorged themselves to ever larger sizes during the cosmic dawn, which began about 100 million years after the Big Bang and lasted a billion years. Astronomers don't know why there were so many of these black holes or how they grew to be so massive. The researchers who discovered the latest black hole have already published their findings. According to said lead study author Rebecca Larson, an astrophysicist at the University of Texas at Austin, this is the first one that we're finding at this redshift point in time after the Big Bang, but there should be many of them. They believe that this black hole did not form recently, so there should be others that are younger and existed earlier in the universe. Black holes are formed by the collapse of massive stars and grow indefinitely by gorging on gas, dust, stars, and other black holes. Friction causes the material spiraling into the gluttonous space-time ruptures to heat up, and they emit light that can be detected by telescopes, transforming them into so-called active galactic nuclei, AGN. The most extreme AGN are quasars, which are billions of times more massive than the Sun and shed their gaseous cocoons with light blasts trillions of times brighter than the brightest stars. And because light travels at a constant speed through space, the deeper scientists look, the more distant light they intercept and the further back in time they see. The astronomers scan the sky with 2 infrared cameras, the JWST's mid-infrared instrument, MIRI, and near-infrared camera, and use the camera's built-in spectrographs to break down the light into its component frequencies to find the black hole. They discovered an unexpected spike among the frequencies contained within the light by deconstructing these faint glimmers sent from the universe's early years, a key sign that the hot material surrounding a black hole was beaming out faint traces of radiation across the universe. It's unclear how black holes appeared so suddenly across our young cosmos. Astronomers are still looking for even younger hypothesized primordial black holes, though, that formed very soon after or even before the Big Bang, according to some theories. However, they have remained elusive thus far. There are 2 leading theories for how so many black holes formed so quickly after the Big Bang. They are the remains of giant stars that formed much faster than the ones we know today, or they are billowing clouds of incredibly dense gas that collapse suddenly to form the all-consuming singularities in space-time. Larson explained that the direct collapse method would have to start with a larger amount of matter in the galaxy collapsing directly into a black hole. It's less likely, but it would take less time, and there hasn't been that much time since the point at which we observed it. More likely, a population 3-star, a category of hypothesized stars that were the first to ever exist in the universe and were made of only hydrogen and helium, exploded and left behind a black hole around 200 million years after the Big Bang, and then accreted a lot of material pretty quickly and occasionally at a faster than stable rate to swell up to the size that researchers observed. The researchers will now begin scanning for an even stronger signature of light from the distant galaxy alongside the team that built MIRI. These emissions could hold more information about how the mysterious black hole and the galaxy's core formed. Astronomers using the JWST have also discovered 4 of the most distant galaxies ever seen, which are about 13 billion light-years away from Earth. According to 2 new studies published in the journal Nature Astronomy, astronomers are seeing what galaxies looked like only 300 to 500 million years after the Big Bang, in the infancy of our now almost 14 billion-year-old universe. Peter Van Dokkum, an astronomy professor at Yale University, said the frontier is moving almost every month. Only 300 million years of unexplored universe history remain between these galaxies and the Big Bang. This may sound like old news, but several studies in recent months have claimed possible detections of even older galaxies using the JWST. The 4 newly discovered galaxies, however, are distinct in that astronomers have confirmed that they are ancient galaxies and not some other celestial body or a nearby galaxy masquerading as a distant one. Color is typically what astronomers use to estimate redshift, a parameter that describes distance as light waves stretch and turn redder as they zoom across the expanding universe. However, when exploring completely new frontiers, such as those being studied with the JWST, this technique is a riskier bet. In what Van Dokkum calls a technical tour de force, the authors of the new study used detailed measurements of the galaxy's spectra, or the range of light they emit at different frequencies, to double-check the accuracy of the redshifts. These 4 galaxies exist during the epoch of reionization, when astronomers believe the very first stars formed. After confirming the ages of the galaxies, the researchers measured their stars and discovered that they were quite small, at least when compared to our Milky Way. but the galaxies were also producing stars at a rapid rate, which was surprising so early in the universe, according to study co-author Stéphane Charlot, a researcher at the Astrophysics Institute of Paris. According to the researchers, these galaxies don't appear to contain any particularly complex elements, implying their stars haven't yet had time to create heavier elements and are instead made of the original hydrogen and helium atoms from the early universe. And yet, given the age of these galaxies, it means they had to grow up fast. Indeed, to put this in perspective, sharks have been around for longer than the universe existed at this point in those galaxies' lives. When the JWST mission was launched in December 2021, astronomers hoped it would find the first galaxies, but results like these suggest that galaxies may have formed earlier than previously thought. Prior to this, just a week after its first images were shown to the world, the James Webb Space Telescope may have found a galaxy that existed 13.5 billion years ago. The galaxy known as Glass Z13 was discovered 300 million years after the Big Bang, about 100 million years earlier than anything previously discovered, according to Rohan Naidu of the Harvard Center of Astrophysics. We could be looking at the most distant starlight ever seen, he explained at the time. Of course, the further away an object is from us, the longer it takes for its light to reach us, so looking back into the distant universe is like looking into the deep past. Though Glass Z13 existed in the early universe, its exact age is unknown because it could have formed at any time during the first 300 million years. Glass Z13 was discovered in early release data from the orbiting observatory's main infrared imager called NIRCam, but it was not revealed in the first image set published by NASA. When converted from infrared to visible wavelengths, the galaxy appears as a blob of red with white in the center as part of a larger image of the distant cosmos known as a deep field. Naidu and colleagues, who comprise a team of 25 astronomers from around the world, published their findings in a scientific journal. Prior to JWST, the most distant galaxies in our universe were GN-Z11 and HD1. As the name implies, the redshift factor, or Z, of the GN-Z11 was 11. According to scientists, it existed around 400 million years ago. However, HD1 was discovered in April and held the record for only a few months. They also looked at a galaxy called Glass Z11, which they thought could be one of the first galaxies ever discovered. Now, these galaxies are small in comparison to the galaxies we see today, such as our own Milky Way. The Milky Way is approximately 100,000 light-years across. Glass Z13 and Glass Z11, on the other hand, are 1,600 and 2,300 light-years across respectively. Both galaxies are about 1 billion suns in size. In comparison, our Milky Way galaxy has about 100 to 400 billion stars. Scientists discovered Glass Z11 while looking into Glass Z13. The two galaxies appear to be pointing in the same direction in space. The scientists do not believe that the discovery of this second, more distant galaxy was purely coincidental. These two objects have already imposed new constraints on galaxy evolution during the cosmic dawn epoch, roughly 50 million to 1 billion years after the Big Bang. They suggest that the discovery of GN-Z11 was not accidental, but that there is likely a population of UV luminous sources with very high star formation efficiencies. In other words, there are likely more galaxies at that distance that are forming stars, which the JWST will be able to detect due to its infrared sensitivities.